angles. But then a larger array would require more elements because there's a minimum spacing that we need to have. And again, we'll see how to reduce that. And then another thing we can do is have many elements transmit simultaneously, and that will reduce the acquisition time, but it will create interference. It might reduce also computational cost. But then we can, whatever they transmit, we can either randomize or code it with some kind of design code, so we're able to separate them. Okay, so these are the main principles. Let's try and apply them to just some simple radar processing problems, and see how they work and see how they apply. So let's talk about array design. We'll think about a standard linear array. Let's say it's a fixed aperture, so that gives me a specific resolution of the array. And I will consider two different cases. One, a uniform spacing, and another one, I'll put the array elements to be non-uniform. Okay? And I will give myself a constraint. How many here are familiar with standard conventional array processing? Okay, so think about it as a sampling problem, right? When you have an array of a certain length, of a certain aperture, you have the equivalent of the Nyquist rate. Everybody knows the Nyquist rate? Okay, good. So you have the equivalent of the Nyquist rate. The Nyquist rate tells you how many array elements you need to put in that array. So if that array transmits at a certain frequency, that corresponds to a wavelength. So you need to place elements at half a wavelength distance. So let me give you an example. Let's say you have an array that operates at around 7677 gigahertz. Half a wavelength is about 2 millimeters. Okay? And now let's say that the array has a size of 20 centimeters. Okay? Well, you have 20 centimeters, you have to put elements every 2 millimeters. That means you have to use about 100 array elements. But that's expensive because every array element you have to sample, do A to D conversion, all that stuff in high frequency, and that can get very expensive, very high, but very quickly. So let's say that your budget constrains you to have 30 array elements. Okay? What are you going to do? Well, you know the equivalent of Nyquist theorem. You're sampling at a third of your Nyquist rate, right? So you know you will have aliasing of your frequencies. So if you make your array uniform, what you see here what you see is what's called the beam pattern. It tells you, let's say I'm sampling and my array is looking, I've set my array to look at the front. How would reflectors that come from the sides appear in my array? So let's say there's something there and something there, something there. For every angle, what maybe you don't see here, if you can see it says this is the cosine of the angle of the array from -1 to 1. It tells you how would an element coming from there appear, assuming I'm trying to look to the front. And if you have a uniform array, you'll see, this is the red curves. You'll see that certain angles, which is where the aliasing happens, are almost as intense as coming from the main lobe. So that means that if I'm looking there, but there's an object there, I will think it's there, or I won't know actually where it is. It might be there, it might be there, and so on. This is because I have a uniform array. The advantage of a uniform array is that it's very well controlled. I can completely understand and make this, and it has very low side lobes. What that means is that elements that are coming here do not interfere, that are coming from in between angles do not interfere too much with my signal. And a different approach would be to create a non-uniform array. In this particular case, in this particular example, what I did is I just randomized the spacing. I created a random, I placed the elements randomly in that 20 centimeters distance. And what you see is that my side lobes increased. The main lobe is the same, but I don't have what's called the grating lobes. I don't have that aliasing. This is equivalent to non-uniform sampling if you're doing, if you're sampling at certain frequencies. But by the way, mathematically, sampling and array processing are exactly identical once you write down the equations in particular form, and you have the exactly identical problem. Okay, so the bottom line here is that you have higher side lobes. If you were to do some conventional processing, what that would mean is that your signal would be a bit more blurred, and if you had a reflector, you'd have a bit more interference on the sides of it, but you wouldn't have fundamental ambiguities. And by the way, this non-uniform array processing is not a new thing. It's not part of. It's not a development thanks to computational sensing. People were doing non-uniform arrays way before. What has happened now is that now we can exploit the structure of those arrays much better than before using techniques that we have. Okay. Next thing is we want to think about the scene model. So let's consider, for example, an automotive radar, just as an example. You have an array, you transmit, there's a car in front of you. Usually when you transmit the frequencies where those things operate, that car reflects and is not penetrated by the radar. So if you get a reflection from a certain distance at a certain angle, it means that there's a reflector there and there's nothing in between. And it also means that anything behind it you can't see. So you might as well call it zero, because you won't see it anyway, right? So you have a scene that not only is sparse, but it satisfies a specific model. Anything in front of the object, as long as you find an object, anything in front of the object is empty, so you call it zero. Everything behind the object is invisible, so you call it zero. So for any angle that you look, you will only have one reflector. You can't have more, because that's the structure of the scene and the model that you're looking at. So there is a very interesting way to enforce this model. It's not coming through regularization. It's using what's called model-based compressed sensing. What you do is you look at any angle, for example, for this particular model, and you only allow one reflector per angle. So you do a truncation that allows one reflector per angle. Okay. So now that we talked about those two things, let's see how they work in practice. And this is an example with a millimeter wave radar simulation. The simulation is in a 2D field. So it's a linear array and it's looking at a 2D field. That's because it's easier to visualize the result. We start assuming a uniform linear array, and we see that effect. And then we compare three approaches: the classical back projection or beamforming or whatever you want to call it, standard compressive sensing using COSAMP, which is one algorithm known for solving these problems, and then using model-based sensing. Okay. So this is the example. I'm guessing you can see the blue and the red. This is the original scene that we're trying to image. This is the angle, and this is the depth. And we're using, in the top line, we're using a 20-element array. In the bottom line, we're using a 15-element array. Okay. So this is the original scene. 20 elements is already small for the array. What you'll see here is, because of the back projection actually starts having blur and a lot of leakage on the side. So even though you have your reflector here, there's significant intensity on the sides. Same thing with those. And COSAMP actually, which is the standard compressed sensing approach, gets confused by that and then tries and gets focused on that reflector. And if you allow it to look for more, it will actually start looking here and not explain the data. It tries to look around this area to explain these pulses. If you use the model-based approach, you can actually, by the way, this is noiseless. My point here is not to tell you anything about robustness to noise or anything. We can have a lot of discussion on that. My point is to show you, even if you have a perfect reconstruction, a perfect acquisition, there are cases where your classical methods fail. And of course, not of course, but you can see that model-based reconstruction actually recovers perfectly. If your array is more subsampled, let's say 15 elements, you have much higher, much more grading loads, much higher blur, and so on. Back projection fails completely, fails miserably. And COSAMP also fails. It actually focuses in this area and explains kind of the data as being from here. Part of the reason, by the way, is that a lot of those inverse algorithms have a back projection step in every iteration. Okay? And then model-based is better, but of course not perfect. But you have a very undersampled array, which is uniform. So that's the uniform spacing. Let's see what happens if we go to a randomized array. Same configuration, same arrays, large arrays, more elements, fewer elements. But now we have randomized the spacing of the elements. What you'll see here is that back projection seems to improve, which is true, but then you see some ghosting. And that ghosting comes from the very high side lobes that exist when you randomize your array. COSAMP now does much better. As I said, compressed sensing is much better at exploiting this randomization than classical methods. And now model-based can recover even with a smaller. Okay? So one key lesson here is non-uniformity, either in randomization or in other ways, helps. And if you know a model, that helps too. Now I have to caution here. Knowing a model is good and important, but whatever you come out will be in your, whatever you recover will be in your model. So in your model, if your model is junk, if you have a very bad model, you will recover junk, and the model will be very confident that it found your junk, right? So keep that in mind. Bad models give you bad results, but you will get something in your model. Okay. Let's switch topics a bit to give you another example of how we can use these things. Synthetic aperture radar. It's a very interesting concept. Has anybody worked on synthetic aperture radar? Doesn't matter. It's very simple. It's the same idea as panorama with your camera, kind of inverted. As you said, the array aperture, the size of the array is what tells you a lot about your resolution. So how can we make a big array? We put it on a plane and we fly the plane, and we take snapshot through the path of the plane, or a satellite, for that matter. And this way, the size of the array is basically the track of the plane. Okay? So you can have, you put the array on the plane, you transmit pulses, and you receive, and you look at the ground, you have the plane looking at the ground. And the SAR acquisition, there's a lot of work on how you recover that, but basically it's a linear equation. You have y equals ax, and how you compute the a. There's algorithms like chirp scaling algorithm, range Doppler algorithm, omega k. There's a ton of algorithms, very good, did some more precise, some more efficient, very interesting algorithms, and very interesting work in this area. But at the end of the day, you have a linear equation. And the image formation problem is given your data, determine x, and invert that a. So I'll give you a brief overview of what's called the modes of SAR operation, and I'm not having all of them. I'm having 3 examples. One is the strip map mode. As your plane goes, the beam keeps looking at the same angle relative to your plane. So as you go forward, your beam keeps moving, so you keep illuminating a different part of the land. So at the end of the day, once the plane flies the whole track, you've just illuminated the strip. And that's why it's called strip map. You've mapped the strip. So the beam is not steered, so every point here is only seen by a few points, a few transmissions of the plane, so you have a smaller aperture, but you cover a big strip. On the other side of the modes of the spectrum, you have the spotlight mode. You always have your beam pointing, and as you move, you keep pointing your beam to the same spot. So that means that as your plane goes on a very long track, that spot has been seen by many angles. So you have a very large array looking at your spot. And this gives you extremely high resolution, but of course it only covers a small spot. Okay. And then there's a sliding mode, which is kind of in between. Instead of keeping the beam completely fixed or keeping the beam completely focused, moving completely focused on one point, you slide it, but not as quickly as the strip map mode. So you have an in-between size of what you're looking at. But you have a higher resolution than strip map because every point is seen by a wider angle, but not as high as the spotlight mode. Okay? And one important thing to understand is that what is the cost on SAR? The cost is not how many pulses you're going to send. The cost is not how much energy you're going to spend. The cost is that you're taking a plane and you're putting up on you're flying a plane, right? So if you can have high resolution but with higher coverage, that means you can save a few flights because you can image the same area with fewer flights. So what you want, ideally, is you want to be very high in resolution but very high in coverage. But the current modes have this trade-off, right? So what can we do to improve this? Well, let's look at the spotlight mode. We know that using ideas from compressed sensing and computational sensing, we can do undersampling. We can use fewer pulses, as long as we use some non-uniformity and some randomization, and then use computation to improve the reconstruction. So what we're going to do is we're going to, instead of looking always at one spot, every pulse will be randomly split between one spot or the other. So we will randomly look at 2 different spots and steer randomly. And this is what we get. Let's say this is the true reflectivity. I don't know if you can see that. Let's say this is the true reflectivity. If you had a conventional spotlight array, you'll get half the image. If you have a random steerable spotlight mode, you get the full image. And this is what it works. This is how it looks when you zoom in. So if you had the full data and you did conventional imaging, conventional spotlight mode, and you reconstructed, this is what you would get. This is, in some sense, considered like the ground truth, the best you can do. Now, you might say, okay, fine, I will split my beams, but I won't do it randomly, I will do it uniformly. This is the image you will get. And I'll explain what you see here in a minute. The other approach would be to randomly steer the array, and then do some kind of wavelet sparsity reconstruction, or use spatial sparsity. Just assume that the scene is sparse in space. Well, what do we see? When you do this conventional reconstruction with uniform downsampling, you see a lot of ghosting. That ghosting is aliasing. It's the equivalent of subsampling at the microstrate. Things in different parts of the region will come and fold back and look like they're here. Wavelet sparsity reconstruction. So this tells you the importance of randomizing or non-uniformizing your array, your steering. Wavelet sparsity turns out that if you have very strong scatters, that tends to activate a lot of wavelets, so it leaks, you have leakage. So big scatters will tend to look like long lines. Whereas if you use spatial sparsity, just simple sparsity in space, you get a much better result. So this tells you the importance of the model. Picking the right model of your signal will give you the good result. You can do the same thing with the sliding mode, or a similar thing. You slide the beam in the area of interest. Well, instead of sliding the beam, as you go through the area of interest, you randomly steer the beam within the area of interest. So you get the same area, but with a much higher aperture, because different points are seen by different parts of the path. And what you see here is, if you look at the results, if that's the true reflectivity, this is the conventional method, and this is the randomized. Remember, now we're not increasing the area, now we're just increasing the resolution. So you get a 10 dB increase in the SNR. You also get a 26% reconstruction in phase error, which is quite important, especially if you're trying to do what's called interferometry, where you try to hide the building. Okay, any questions on SAR or something? Okay, good. So we talked a bit about radar and array processing. Next thing I'm going to talk about is distributed array processing, and we have a lot of interesting work and results there. I'm not going to talk about all of them, but let's think about what is a distributed array. So what was the lesson we learned from the previous set? Well, aperture is important. How do we get a big aperture? We can fly a plane, we can make a big physical array. Another way is to actually have a few small arrays and just send them using either drones or just plant them everywhere. Just spread them around. And so you get a very large size of the array, so you have very high resolution. And you have very small and cheap platforms, which are easy to maintain. And if one fails, you have the other one. So it's much more robust and fault tolerant and inexpensive and low maintenance. These are the benefits. But there's always a but. When you're sampling at those rates, you need very high clock precision. So clocks are difficult to synchronize. Also, think about drones, right? You have your drone. How does it know its position? Well, maybe you can put a GPS signal. It's never good enough. So your position of its platform, the position of its platform is never accurately known. When you're talking about, let's say, millimeter wave, you need the position known to sub-millimeter accuracy. So you need the position known to tenths of the wavelength to be able to do good reconstruction. So this is the drawback, and then by having a large array, you get a very big aperture, very high resolution potentially, but you need to spend a lot of effort synchronizing and knowing where you are, where your array is. So can you use computational methods to improve that? Let's look at the first problem, imperfect synchronization. The main intuition is that when you transmit something and you receive it, if the receiver clock is not fully synchronized with the transmitter clock, the receiver clock will timestamp it with a different time than it should be. So it will introduce a delay or an advance on what you think is your signal. Okay? Well, what is a delay? A delay is a convolution with a one sparse signal. It's a signal with all zeros. If there's no delay, there's an impulse at 0. If there's a delay somewhere else, that impulse just moves. So we can model that. We can get the array. If you look at the transmitter-receiver pair and the relative clock error, we would get the ideal data convolved with that impulse, that ZM, where that ZM is a one-sparse signal modeling that time delay because of the clock error. Now, that problem is actually nonlinear because you have that unknown. This is something you don't know, right? It's a clock delay. So you'd like to recover this and this together. But that unknown is convolved with this signal, so it's it's multiplicatively involved with this unknown. So you have a nonlinear problem, but you can do tricks. One trick you can do is bring that unknown to the other side and say, well, I will not try to advance or delay my ideal signal to explain the data. What I'll try to do is try to shift my data to be compatible with the signal I recover. Right? So you bring that here, so it stops being multiplicatively entangled with X, and then you bring AX, or you bring that to the other side, and you say, well, this system, if I take those two unknowns, this system should give me 0. Okay? Or you can write it in this form, and you say you have a matrix which is, so here, you take that in the Fourier transform so that this becomes a multiplication, and you can multiply y on the other side, but at the end of the day, you can get a system like that. I can tell you the details. Well, A tilde incorporates y as well, okay, and expresses data in the frequency domain. And then what you want to do is you want to get the solution that X is sparse and Z is sparse as well. So what's the sparse solution to this problem? What is an obvious solution to this problem?
0.
0. So I'm in trouble again. So just formulating the problem to be a linear problem is not enough. We need some additional constraints. What do I know? I know that Z's are delays. So delays are positive and sum up to 1. So it's going to be a 0 vector with only one non-zero. So I'm going to enforce it. Positivity is a convex constraint. Summing up to 1 is a convex constraint. My signal typically will be positive and non-zero. And actually, this is an artificial constraint that you need to add and help the solution. So to avoid the trivial solution, which is the all zeros, you can add those constraints. And at the end of the day, that's what you get. You minimize the L1 norm of X and the L1 norm of Z subject to, and Z, by the way, is you have a different delay for every pair of transmitter receivers because they're all unsynchronized, so they induce different delays in the system. And so you have this big problem, and you can solve it again using standard methods like that. So let's see.
Sorry to interrupt. What's the last line?
The last line?
No, the the
Oh, the last line enforces that X is non-zero. So it says that X is equal to some constant. The sum of X is equal to some constant. X is positive, and that constant, there are ways to estimate or find it, depending on how, and the gamma is kind of like a regularization weight, a parameter. There are ways to find it.
Enforce it exactly.
I don't enforce it exactly because I don't know it exactly, but I have ways to estimate it maybe. And I want this to be a soft constraint because I never know it exactly. But one important thing is that this is the line. I mean, there are these constraints additionally, but this line makes the problem not be a simple null-space problem. Okay, so this is an experiment. These are 32 antennas split into 4 arrays. We use a 9 gigahertz bandwidth differential Gaussian pulse centered that's wrong. It's a 6 gigahertz bandwidth differential Gaussian pulse centered at 90. Every time I give this talk, I discover a new mistake. And the timing error is up to 1 nanosecond. This is, and the array actually, again, another mistake I just realized. The array is actually at the right position where we think it is. So you just look at the dots, forget the x's. The array is where we think it is, but the clocks are unsynchronized. Okay, so this is the original scene we want to image. This is the array. There's one antenna moving this way and transmitting, and then all the antennas are receiving. Again, look at only the dots, forget the crosses. These will show up later. And we're looking at that image here, which has three reflectors. This is the original scene, and there are many ways we can deal with the problem. One is just ignore the timing errors. Well, if we ignore the timing errors, then I mean, you get something. I'm not sure if anything is recovered, but basically you get junk. Or you can perfectly synchronize your system. If your system is perfectly synchronized, you need to do it to very low, very high precision. Then you actually recover a very good image of your reflectors. This is what the scene is, and this is what the image is. The problem is that you can't in practice synchronize your signal. If you use our approach to correct the timing error, then what you get is reflectors in the right positions. Those reflectors are sparser than this. This is a side effect of the sparsity we impose. There's no sparsity imposed here, but this is easy to modify and get it to look like that, or get this to look like that. But the point is that you get the reflectors at the right position. Okay? So that's a timing error. We can look at ROC curves, so receiver operator characteristics, false positive versus true positive, and you see, I guess my battery's dying. So at the top you see what happens if you have small timing errors, and and on the bottom if you have large timing errors, and on the left, sorry, on the left you see what happens if you correct the timing error, and on the right if you ignore the timing error. And as you can see, it always pays off to correct the timing error. Of course, nothing is perfect. Well, if you have larger timing errors, you're gonna have worse ROCs, even if you try to correct them, than if you have smaller timing errors, because you have less ambiguity. So if you can afford to synchronize your clocks a bit better, and that's where the trade-off is. The more you can synchronize your clocks, the better, and the less computation and the better performance you can get. But at some point, it becomes too expensive, so you have to rely on more computation. Okay. By the way, if you have large timing errors, the problem does become larger. But you see, you get pretty good results, even down to here, even down to 8 dB or 10 dB SNR, which is pretty low SNR for radar. Okay, next problem: unknown positions. It's a very similar idea. Your transmitters transmit to the scene. The scene, again, is a sparse image. It's unknown. So for every transmitter-receiver pair, you get the data is equal to AX. And then what happens is your transmitters are not where they think they are. So you think your transmitters are here and your scene is here, but actually your transmitters or the receiver is shifted. So what happens is the data you're going to get is actually the same thing as if the transmitter is where you think they are, and the scene was moved in the opposite direction. Think about it, right? I have a transmitter and a scene. I have a radar and a scene. If my radar is actually here, and that's a daytime recording, that would be equivalent if the data was here and the scene was there, because it's all just shifting variant globally. Right? So what you can do is actually take the scene and model it as a scene convolved with a spatial domain impulse, which reflects the 2D shift of the scene because of the unknown position, measured by the radar operator. Gives you the data. And you can do that for every pair. Again, the system is underdetermined, but we know the shift kernels are sparse. Again, one sparse. The scene is also sparse, and we can still formulate it as a minimization. So what you do is you want to recover X and H by minimizing this cost and imposing sparsity on H and sparsity on X. And you want, again, that the sum of H's, because their shift kernel, are 1. This is a more difficult problem to solve. You see here, we have again this coupling between H and X, this nonlinear coupling, which in this case we cannot break as easily as we did in the previous case. So what we do is we alternate. It's one method. There are many methods to try and solve this. But this seems to be the most efficient computationally, but the least easy in terms of theoretical results. You basically can't provide many guarantees. It's a non-convex problem. It's harder to solve, but you alternate between H and X and solve for H and solve for X, and keep going back and forth. And keeping one constant, then the whole problem is linear, and that's why it's called a bilinear problem. Let's see how it works in practice. I'll move closer because my clicker has stopped. Again, 32 antennas split into 4 arrays. This is now the problem. We assume the antennas are perfectly synchronized. Of course, you can combine both and have timing and position errors at the same time. But let's say that now timing is perfectly synchronized. The arrays think they're here, but they're actually where the crosses are. Okay, so you see the crosses, this is where they actually are. So at every point, this transmitter transmits to the scene, and they all receive the reflection, including this transmitter. This is the actual scene. This is what you would recover if you exactly know the position errors. And keep in mind, we have very large position errors. The average position error is 2 wavelengths, and the maximum error is 3.5 wavelengths in this simulation. So it's pretty large position errors. If you know exactly the position, you get very good recovery because you have a large array. If you ignore the position errors, you get nonsense. There are some techniques that try to do what's called the phase correction. So you look at the data, you try to change the phase in your data to correct the position errors. They don't work very well because you don't have a good model of how the phase changes to fix that. And it's not just a phase change, you actually, it's a difficult model to work with, and actually they don't work well. But if you use that correction we mentioned, you get very good localization. Now, one thing you'll notice is that this scene is shifted compared to that scene. And that's because there is a fundamental ambiguity. I can always shift all the arrays by a certain amount and all the scenes by a certain amount, and I get the same data. And I cannot resolve that. One way to resolve it is to assume that the average shift is 0. We haven't done that, and that's why you get that shift here. And it's not easy to enforce immediately in that optimization. You have other ways to do that. But that gives you just the result of this optimization. So you get a small shift. That's because of that fundamental ambiguity. And then you can do ROC curves, and again, you see that if you ignore the position error, you don't get a very good ROC curve. Even if you do phase corrections, the ROC curves are not that good. If you correct the position error the way I mentioned, and you make sure that things are, the errors are zero centered, you get an ROC curve that even for 8 dB SNR, which is very, very low for radar standards, is pretty good and fairly consistent among with all the other curves. And then it goes down for 6 and 4 dB, which is pretty high noise. Okay. These are experimental results. So we said, oh, that works. Let's try it in the lab. So we took a radar system. We positioned it, taking measurements. We put 3 big cylinder pipes to image. And then what you'll notice is that the true positions, the X's, in those antennas, not the transmitting antenna, but in those antennas, are shifted compared to where we think they are, or where we would like them to be. And this is a very interesting. This is a very interesting case. So we intended when we did the experiment, we intended the blue dots to be in the middle. And we tried the results, and we run it through the algorithm, and the algorithm gave us this position for the blue dot, for the axis compared to the blue dots. And then we went back to our notes and realized we had made a mistake in our experiment, and our algorithm corrected that. And it's a pretty significant position change, but our algorithm was good enough to find it and correct it. So this is if you have the true positions after. Of course, we realized our mistake, and we actually put the true position in the algorithm. You get a very good reconstruction. It's pretty accurate. This is if you ignore the position error, and what you get, like these crosses are not really reflectors. It's more like interference patterns from the arcs that you get because of the ambiguities. And if you correct the position errors, you get the 3 reflectors fairly well. Of course, it's not perfect, as if you know the position errors. It's a fairly good, fairly accurate.
You're considering reflection. Well, it's a measurement. So you had reflections.
It's a true measurement. Yeah, we have reflections.
It wasn't an anechoic chamber.
No. And actually here, what is interesting is that because of the shift, here what you see is a bit of a, the back corner of the room that happened to have like 3 beams connecting, and it was one more corner reflector. So no, it wasn't an anechoic. It's a true measurement, and that's why you get some multiple reflections or so on. Okay. It wasn't a very dense room. It was an empty room with the array, but it wasn't an anechoic. Okay. So we talked about computational sensing principles, radar and array processing, distributed array processing. Let's see how these things apply a bit to LiDAR sensing, and you'll see some other aspects of this problem that are very interesting. So what is LiDAR? You guys have heard of LiDAR, right? You send light,
Yes.
gets reflected. It's the main principle. You send a pulse of light, gets reflected from the scene. You sense it, and then by trying to measure the delay of the pulse, you can figure the distance of the scene, right? It's a standard, very easy principle. So you just need to measure the time delay and divide by the speed of light, and then you're done. Well, the problem is how to measure the time delay. That's the real problem right there. And when engineers say how, we can measure it. The problem is how do we measure it cheaply? That's the real problem in these systems, right? Because we can always have very expensive equipment, but if that has to go on every car on the road or on every imaging system on a plane, that's very expensive. Okay. So let's look at what's the state of LiDAR, and I have to admit this is a bit of an older slide, but the ends of the spectrum haven't changed too much. So you have on one end you have the Velodyne, which is what Google uses on the Google autonomous driving cars, and they use to do the car that does the Google Maps and everything. This is a very high-end system. It scans. It uses a mechanical. It uses a motor to scan the array. It has 64 lines. Now they came up with a 128 lines one. But it turns around and scans and sends pulses and measures the distance. A lot of mechanical components. It's very good for working outdoors, very long range, high resolution, and so on. But it's very, very expensive. When I was doing that research, which was a couple of years ago, Velodyne came out with a new cheap system, which is affordable, and it's only $8,000, right? Of course, that's not something you can put on every car on the road. And this has 8 lines. At the time, and price has gone down a bit, but at the time it was basically $1,000 per line if you want scanning, if you wanted the LiDAR. Okay. On the other side, everybody knows the Kinect. Microsoft Kinect has a depth sensing camera, Xbox exactly. The Kinect, the first Kinect was a structured light camera, so it doesn't qualify as being in that category. But the next generation was time of flight, so it would send the pulse to see how long it takes. It would use custom solid state components, but it was indoor use only. Very short range, not very good with background lighting, a lot of lighting, moderate resolution, and only had a 60 degrees field of view. But it was only $100, and that includes the packaging and everything, and Microsoft's profit on top of that and all that. So it's very, very cheap, and there are newer devices now that are essentially the same principle and have come even further down in price. But of course, the specifications are not something we would like. So the goal is, can we work somewhere here where the price is not as cheap as Kinect? I don't expect we will do that. But the specifications are, it's a bit higher, but the specifications are much higher. Of course, probably not as good as the Velodyne, but it might not matter if you can drop the price very well. Okay, and I'll tell you things that we've done, and we've learned a lot from this process of trying to develop that. So we're looking at pulse time of flight. So you send a pulse to the object reflects it. The amplitude of the reflected pulse that you receive depends on the reflectivity of the object and the distance of the object, and you get the time delay that has to do with the object distance. And so one technology of time of flight sensors array that use pulsing is they use a fixed pulsing laser and they illuminate the whole scene. So you send a big pulse everywhere instead of the Velodyne that scans. The Kinect does that. The Kinect doesn't use a pulse, it uses a continuous wave, but you send a big pulse to the whole scene. That scene reflects the pulse, and it comes back, it goes through a lens, and that focuses the pulse, the reflection, to a time of flight sensor array, which if you want a 10 megapixel depth sensor, you need a 10 megapixel sensor array. For every sensor, you need analog to digital conversion and so on. Okay, so this is very expensive. It uses a lot of sensors, a lot of A to D converters, and that's why some people use scanning to reduce cost. But let's look at that basic system and fundamental system. This is the architecture we want to start with and then try to improve upon. Okay, so can we improve that? One idea that was not initially ours was to put a coded aperture here. So what is a coded aperture? You put something that blocks part of light, and you put it in a way that also defocuses certain things. So your light is not sensed by one sensor, but it's sensed by multiple sensors. And by doing that, you can do that mixing I was mentioning in the beginning. And then you can use a smaller sensor. And when I say smaller, I'm not necessarily talking about the size, the physical size, but the number of sensors. And then each sensor in here senses multiple pixels. So it gets a linear mixture of the reflected pulses, and the system is in some sense compressive. So the spatial resolution depends on the coded aperture resolution and the scene structure we can exploit. Okay. So how to do that? The first approach was using a digital micromirror device. This is very similar to what they have in the projectors. It's a small chip that has a lot of tiny mirrors that move very fast. Not as fast as we would like, but very fast. And it was called Kodak. It was done by Kirmani et al. In Vivek Goyal's group at MIT. And it's very similar to the Rise single pixel camera in terms of architecture. The good thing with that system is that because this coded aperture changes patterns, and you can sense the scene with multiple patterns, you can use a single time-of-flight photodiode. Your sensor can be reduced to one. But the main drawback is because you need to change the pattern of your coded aperture, every time you change your pattern, you have to wait for the mirrors to settle, then you have to send the pulse and so on. So it's very slow, and actually the device, the micromirror device, is very expensive. So it's only practical for static sense. It's cheaper than the photodiode. Your projector has these devices, so you can imagine that it's much cheaper than the photodiode, but it's still expensive. Another approach would be that what we took as an approach is we replaced that aperture. Instead of having a variable aperture, we replaced it with a fixed coded aperture. These are cents. They cost cents to print. Basically, you take a transparency and you print black or transparent on it, or you take a metal plate and you cut holes on it. That's all you need. Can be printed very cheaply. There's no need for this digital micromirror device. And it allows for a single shot acquisition because you can't change your aperture. You can send one pulse and receive the data. The drawback is instead of a single sensor, now you need a small array. So the cost moves from the DMD to the analog to digital converter for each sensor, and the cost is sampling again. It's cheaper than a large array, but not as cheap as we would like. Okay, so this is kind of the trade-offs. This is what we would call the conventional. Very, very high price, very low complexity, because as soon as you get your image, you have it. Kodak drops the price a bit, but increases the computational complexity a bit. And then our approach, our initial approach, drops the price more, not as low as we would like, but then it requires a lot of complex computation to work. Okay, so again, our goal is to reduce the price further and reduce the complexity further. And the key realization here, when you look at those systems, and that comes back to what I was telling you in the beginning. When we say cost, we need to understand what is cost. Photodiodes are cheap. Light modulation is cheap. High-speed analog to digital, analog or binary multiplication is also cheap because your cell phones do it all the time. Analog to digital converters at those frequencies, sampling frequencies, are very expensive. So what are we going to do? We're going to use those liberally. We're going to use actually a lot of sensors, but we're not going to convert them. We're not going to use a lot of converters to do that. How are we going to do that? We're going to replace converters with computation, and we can do that in hardware. This is the system that we're going to talk about. We're going to transmit a pulse. Now that we can code the light coding is cheap, we'll send a pulse that is coded, and that's important. This will go through a lens. It will go to our array, which is now a dense array, which can be as cheap as your CCD or your CMOS detector. And then each of those sensors will get multiplied very quickly with a binary pulse. We will code it. It's something that people doing communications, it's very easy to transfer here. And you can code it at a very fast, very high rate. So every input, every pixel has been multiplied with its own code. Okay? And then we add everything together, and then we use a single analog to digital converter to sample the signal, which has to be a high rate analog to digital converter. But actually, doesn't need so we modulate the transmitter pulse and the reflection. In particular, the ADC, although it has to be high rate, it doesn't have to be high bit rate. So we can actually even use a 1-bit analog digital converter, which is just a switch. And those can go very fast. Those can go at more than gigasamples per second. Okay. So in some sense, the system here that we do is effectively the same as replacing that digital micromirror device, but doing it electronically with those coding sequences. Okay. Okay, so we can go. I guess I'm not gonna go through that because it can get very tedious very quickly. We can transmit. We can see what's the transmitted pulse and get the received pulse and then modulate it, and we get a system like that. And after sampling, we essentially get this kind of linear system. But let's see how it works with the scene model. We discretize the scene in 3 dimensions because remember, if you have a delay, your delay itself is not easy to estimate because it is not linear in what data you receive. But if you make your model like that, your scene is a 3D scene now instead of just trying to recover amplitude and distance. Your scene is now sparse, and you can add a model. You can say, let's say it's sparse in depth, or there's one reflector in every direction. So you can actually take that model, and then your acquisition is linear. So at the end of the day, you get y is equal to ax, okay, as we've done before. So you get the pulse gets convoluted to the scene, comes back, gets multiplied, sampled, and so on, and summed. But at the end, you get a linear system, okay? And we've managed to convert that intensity and depth to a linear system. So what do we know if we use a linear system? We'll use compressing, sparse recovery, L1 optimization, whatever you want. There are many options. Unfortunately, if you would try to do that and do it in a car, you'll take a snapshot, you'll try to recover it and feed it to your mapping algorithm, you'll have crashed by then. So we want to do here, computation is not very cheap. Because computation in cars is expensive, and we're talking about a very big model. So here is a case where we actually want to do simple computation. As I said before, we have to think about our trade-offs. So we can actually do a back projection and thresholding. And how do we do that and make sure that this works well? Well, we make sure that this operator is a good one. So we use longer pulses, which we can afford. We use a lot of good coding and things like that. We do some computation in implementing that operator. Some of that computation is done in hardware. So we've moved some computation in hardware where it's actually cheaper than trying to do it in a DSP for this particular case. Right? So again, thinking about the trade-off is important here. And at the end of the day, you can do simple, essentially beamforming or back projection and thresholding. So for example, let's say you have a 30-meter scene. You want to look at 30 meters with 3 centimeters depth resolution and a 1/4 megapixel camera. Even if we do 5 times oversampling, we can achieve a frame rate faster than 40 frames per second. And these are examples. This is the length of the pulse in terms of samples, which affects how many frames per second you can get. If you have a short pulse, back projection and thresholding doesn't work very well. And the longer you make the pulse, the better it works. Of course, if I were to do inverse problems and things like that, like very sophisticated methods, I would probably even here I would get good results. But it wouldn't matter because I wouldn't be alive to see them. So the bottom line, it works pretty well. Okay, I'm concluding. So we talked about what computational sensing has brought into the array processing. And I told you about the principles. If you have any questions, I'm happy to talk more about them. There's a lot more. I mean, it's a very rich field. It started with computational imaging and compressed sensing, and it's been going on for 15, 20 years. And there's a lot of theory, a lot of practical examples. I've omitted a lot of work that isn't kind of on the sides of that, but I'm happy to talk about a lot of these things. And what I meant to show with these 3 applications is that there's a lot of applicability. There's a lot of things you can do with this framework, but you have to be aware of the costs and where it's what you're saving and what you're compromising. Okay. My take-home message is that computation, this is the main take-home message, should have a symbiotic relationship with sensing. It's important to balance the trade-off between hardware complexity and computation, but you have to think about those two together. It's not just signal processing, or it's not just hardware design. You need to think about both. Good modeling of the signal and the system is key. And keep in mind, bad models will give you bad results, right? And the other thing to know is that linearity can go a long way. A lot of the times, you see systems and they look very nonlinear, but with very simple transformations and maybe sometimes a small expansion in dimensions, you can convert them to linear. This is something we did with LiDAR. By taking LiDAR will typically give you intensity and depth. Well, we made it a 3D scene. That's a big expansion size, but it makes the model linear. With our timing errors, we just move convolution to the other side, and we converted the delay again to an impulse. That was a small expansion in size, but it makes the problem linear. And then the whole framework of inverse problems is very powerful and very generic, and it makes model enforcement very easy. And by the way, this is not just a linear framework. We have a lot of work which is very similar to what you guys are doing with seismic, as I mentioned, that can be applied to nonlinear models. Okay, so I'm happy to take any questions or any comments that you have. Thank you.
Please, if anybody has any questions.
I was very curious about LiDAR development. Could you give us a little bit more detail on the development of hardware and how do you acquire the signals?
So we haven't done. We had a different project to try to do hardware development with another architecture that, because of certain manufacturer delays, we ended up abandoning. We haven't. So this architecture, we haven't implemented. It's actually, we're looking at how to implement this. One of the problems with implementing that is that to do it, you're much better off doing it on design a chip that does the whole thing, and we don't have that expertise in the lab. But we have implemented a very similar architecture with fewer channels, but the very, very same idea. And actually, it's interesting. So we've implemented that for communications, and it works very well. And we've demonstrated that and so on. And what is interesting is that we developed this architecture, and the communications group developed their own architecture. Very separately, we weren't talking to each other. And at some point, because of some restructuring, we happened to find ourselves in the same group. And then they talk, and we're like, oh, that's what I'm doing. It's like, oh, that's what I'm doing. I've shown this. So if you want to look at the hardware, what you need to do, so your photodiode needs to be able to respond at the timing that has to do with whatever depth resolution you have. So you think about light travels at a foot per nanosecond. Okay, so if you want a half-foot resolution, you need the sub-nanosecond, because it's round trip, right? So 1 foot round trip is half a foot distance resolution. You need sub-nanosecond response. You need to be able to send a nanosecond length pulse. That's your implicit Nyquist rate. Okay, so you need your photodiode to respond to that speed. That's easy. There are many people use photodiodes like that for optical communications that go 60, 100 gigahertz, and so on. Okay, gigabits. The next part is those multipliers. There are very good multipliers that can do this process, and you don't need actual multiplier with any arbitrary wave. You need 0-1 multiplier or 1-1, and that is a switch. You just do it with a switch. Again, this can be done, and it's been done in communications at those rates, like 60 gigahertz or so on. So you're very well off there. Then another, that's just also easy. Your problem is the A to D converter, because you also need your A to D converter to run at that frequency. But again, if you go down to 1 bit, that's still just a comparator. And you have comparators that run at 60 gigahertz. I mean, I can show you the spec. The problem is that if you take all that and you buy separate components, for example, this photodiode, if you buy a photodiode that satisfies the speed that you have, it will be a big photodiode for one thing. and it will be $1 per photodiode. Okay, so once you do a 64 by 64 array, it starts becoming very expensive. Multiplier, same thing. But the cost is not really the photodiode, the cost is all the packaging and the shipping and all that. And that's why it's much more cost effective to build one chip that does everything together. It's just we don't have that expertise. So what we're trying to do, we don't have an official project, we're done with this, but we're trying to do kind of a stealth mode and see if we can try to do a very small scale with discrete components and kind of prove the concept.
Nice.
And then pass it to the parent company, which has much more resources to develop that.
All right, thanks.
In this topic, was wondering, you are actually coding the light when
Yes.
you're transmitting the light. Would it make sense to use to do the coding after the diode?
No, no. What do you mean after the diode? You mean at the receiver?
At the receiver side. Yeah.
No, the problem is that, so if you transmit a pulse and you receive it, you need, if there's a different delay between here and here, let's say you sample at the pulse rate that you transmit. You don't have enough diversity in what you transmit so to be able to distinguish between the coding that you're adding versus the effect of the scene, like the attenuation of the scene. And if you could, after the diode, for every diode, convolve with the code, but that's very expensive. It's easier to just put photo transmitter that turns on and off very fast. It's easy, like a fast laser.
Okay, I was thinking that could maybe be cheaper, but then
No, because you need to convolve a signal in time. How do you convolve a signal in time? And with a different filter, it never responds. Oh no, actually the same filter never responds. How do you convolve an analog signal? There aren't many good ways to do that with a random long code. Okay, that's why you put it here. But it's a very good point. It's a thinking that we had, like where do we need to put everything to design the system with computation in mind. Now, another thing that's interesting is when the codes become very long, randomized codes work. But you might be able, and sometimes it's better if you use a design code, like an M code or something. What you need is that the code with itself needs to have very low autocorrelation, except for the zero lag.
really something like rolling codes.
Yeah. There are a lot of designs that satisfy that. And then you need these codes to be maybe orthogonal to each other. That would help, things like that. There are many things you can do to improve things other than randomized. But once your system gets very long in code length, then randomization is actually pretty good. One of the difficulties with randomization, if you don't do it correctly, is that you need to store all those codes somewhere, and that takes a lot of space and a lot of computation to apply. And that's where actually smart code design can help you. Not necessarily to improve the performance of the code, but to improve the computation of the code. Yeah.
Further questions?
Still on the same topic.
Yeah.
You mentioned randomized codes and M codes and design codes. And I understand that the code should be orthogonal so that you can use the adjoint to...
They need to be approximately.
Yeah, right. So you can use the adjoint. But why do they have to be long? That's
Well, so
something
the problem is that they need to be orthogonal to shifts of themselves.
which you can
Wall
also
shifts
get,
of themselves.
which you can also
But you
get in
can't-
design code.
You can't get them. Here's the thing: you get your code. What you get here is not just your code; is your code multiplied with this. So you need the product of those two codes to be orthogonal to shifts of that code product with the same product. So I'm sorry, I didn't get that. So, yeah, that's what. Sorry, that's what we mean. Let's use the board.
It's kind of like CDMA system.
It's kind of like
It's
CDMA,
exactly
but
like
you also have
CDMA.
the depth component, and that's what kind of. So you have let's say you have a reflector here and a reflector here, okay? A different pixel. So this is one pixel, this is the other pixel. And that gets multiplied by a different code. Okay. So what you will receive at this point is your original pulse delayed I'll just do a wide thing. This is your original pulse delay, and at this point you will get your original pulse delay by less. Okay. Now those are the same before the modulation. Okay. So with the modulation, you will take that and multiply it with your chipping sequence. Okay. Now if that was here instead, then what you would get would be closer, right? And you are matching not to this code, but to the code multiplied by this. So this code will be multiplied with a different shift, with a different part of this sequence. So this sequence could be orthogonal, but it's not sufficient because you need to multiply back, so demodulate, and then convolve with that code. And at that point, the code has been been distorted by that modulation. So you might be able to get perfect orthogonality, but I'm not sure you can. And it turns out that randomization works well. The M codes and things like that work well, as long as those codes are incoherent with your pulsing sequence. So there isn't any part of the code that's exactly identical. And the longer you make the pulse, the easier it is to achieve that. You might be able to design things, but I haven't been able to find something that works well under all those. You have very few codes and degrees of freedom compared to the number of pixels that you're trying to recover, and every pixel has a different signature to be able to make everything perfectly orthogonal. Unless you start doing a lot of oversampling, which you can, and then it can become orthogonal and you can invert. But I'm not sure how easy it would be to design.
Se alguém preferir fazer a pergunta em português,
Maybe to say something else. In many ways, the way I think about it is that you have a fixed set of degrees of freedom. Same way with arrays, right? You can push the side lobes a lot, but you can't make them absolutely zero. You can't make an array response to look like a pure impulse.
well, that's what you get with heavy codes.
Yeah, exactly.
You make them longer, they will reduce the
Exactly.
correlation.
And that's the same idea. It's just that now you have this coupling, which makes it a bit trickier. And that's why even with M-codes, you have to make them longer.
You guys wanna? Okay. I have one question now, moving a bit outside of your talk, what you've been showing here. Many of the people that are here, they are working with audio. So, and of course, most of what you talked here can be applied to audio. But could you tell us a bit what the audio group in Bureau is doing?
Yeah, so we have a speech group. It's called Speech and Audio. I have worked with them in the past, by the way. Some of the work we have done in the past involves not reverberation, sound localization, beamforming with microphones and things like that. Because you have a passive system there, you cannot control your source, so you cannot do things like some things that I showed. But there are other ways you have a broadband system, so that's a good thing. So you can do things like joint sparsity.
Why do you consider broadband a good thing?
More diverse. The more in all those.
It makes adjusting the beamwidth your array much more complicated.
Well, but you're not trying to do it by the beamwidth. It gives you, so you can have an array that is not spaced at the minimum wavelength, because you have the high frequency, as long as you have high frequencies and low frequencies. All right, I'm not talking like that. But have a range of frequencies. You can use the low frequencies to essentially eliminate the grading load, because at the low frequencies you don't have grading loads. And then you can use the high frequencies, which give you very good localization. So you can combine the two and get that diversity and figure out where you are, even if your array is not exactly spaced at half a wavelength of whatever is the highest frequency. And we've done that a lot, and it gives you very good results for localization. You can even try and think about how reverberant environments would affect your, that gets trickier. This is older work. Now our speech and audio group it has jumped the bandwagon of deep learning. So they're doing a lot of learning, they have a lot of data, but the ideas are, the problems are basically the same. Reverberation, not beamforming, like array, acoustic array, and cocktail party problem, you know, source separation, even with one microphone sometimes.
Thinking on hearing aids or?
No, we're mostly about speech interfaces. So the other thing that the more recent work, which is actually very impressive, is they can do multilingual speech separation. So let's say you're speaking Portuguese and I'm speaking in English, and we had a friend. But Portuguese they hadn't incorporated, but they gave a demo with French, English, Japanese, and other trying to incorporate Chinese. And they were all speaking at one microphone at the same time and asking questions on the system, and the system was responding to all of them, which was quite impressive. I'm always impressed with speech guys. They always have very, very nice demos, and then there's a lot of good work that goes into those demos. But yeah, noise reduction, especially if you think environments like automotive environments and things like that, where you might have rain on the windshield, and you might have the windshield wiper, and then your air conditioning has noise. There are some benefits in automotive environments that you have a bit more control of where you put the microphone, as opposed to letting the user put them. And you kind of know where your users are. You know, there's a driver and a passenger, and then 3 seats in the back. But there are other difficulties. It's a much harsher environment, a lot more noise, you know, tire noise, things like that. They've also started looking at some scene understanding and multimodal scene understanding. So understanding audio and video together, and trying to give description, captions, and things like that.
That goes with deep learning, right?
I don't think they have a single project that has a deep learning nowadays. And the key to that is having data. And it turns out that speech and audio, at least the applications we're looking at, you can collect a lot of good data, so that makes things easier. They've done, you know, they're not blindly applying deep learning. It's not one of those things where you just take the network and training. They've done some work on what's called deep unfolding. So if you look at earlier models, probabilistic models, you can write them as an algorithm, iterative algorithm. You unfold that algorithm, and there are certain parameters that are typically tied in the algorithm. You let them loose and you represent that as a network. So then you kind of learn a new algorithm together, starting with an existing one that you know performed recently. That gives you good results. This is actually something that has been happening in our community as well. So you look at this iterative algorithm, the L1 recovery, right? If you think about the simplest version of that, which is iterative soft thresholding, it's a linear operator followed by the soft threshold by linear operator. You can take that and say, I'll do 40 iterations. That's a 40-layer network. And then you do back propagation to that based on data to see if you can improve. And people have shown very, very good results.
It's kind of learning the adaptation of your.
Yeah, it started with a paper called Lista. Well, the paper is not called Lista. It's Learned Iterative Soft Thresholding Algorithm. One of the 3 big ones, I can't remember Kuzyama, I think Kuzyama is one of the authors. And then he had that idea of unfolding ISTA, which is iterative soft thresholding, and learning it. And now there are a ton of variations. You can incorporate a linear layer in the beginning which models you're assessing, so you can actually learn what is a good A. You can do the same thing and impose sparsity, and you can effectively do dictionary learning using deep learning. So there's interesting work in this area beyond the classical deep learning ideas. And we're starting to look into that. But the speech team is almost exclusively deep learning.
Where else would you apply machine learning, deep learning in your?
So a lot of the things in the project I showed, we don't have too many. I think one critical part is learning the models. So a lot of our models right now are sparsity and dictionary learning to learn where we're sparse at. Autoencoders have been proven to give you very good models for certain kinds of signals. So you can use those and combine them with your measurement system. There's work, not in Merle yet, but there's work outside that shows that you can take an autoencoder and use that as a model instead of a sparse one. Use that as your regularizer. In fact, there's some very interesting work which is based on the concept of deep image priors. Have you guys heard of deep image priors? The idea is that what really captures the nature of images is not really the trained model, but the structure of the model. So what people do is they use untrained models that have the convolutional structure, the multi-layer convolutional structure, and they find the parameters that explain your data without having any training. Like they don't pre-train the model, and they turn out to work extremely well. It's just in some sense surprising, in some senses not. Then there are other approaches which are hierarchical sparsity. Mickey Lab technique has done something like that, which tries to explain some of deep learning using sparsity concepts with different hierarchies. He doesn't call it hierarchical sparsity, he has a different name. It's essentially the idea. So there is interesting work on getting learning in models. I'm trying to think where else. Sometimes, and that's some work we've tried to do, sometimes it helps to learn ways to precondition the system, like massage your data to make distribution faster or easier. Also, sometimes it helps to reduce the number of iterations of your algorithm, even if you know the model.
So just sort of pre-widen.
Yeah, something like that, but with preconditioners that you learn. Yeah, these are the areas. Our team does not do detection and estimation or classification in the classical learning sense. So a lot of what we do needs to be applied in this inverse problem. Actually, we're starting soon a project that will look much more deeply into that.
Interesting. Questions? No? So to thank you for coming here, we would like to give you a mug from our
Thank you very much.
lab. That's the lab that completed 20 years last year. So
Thank you.
Thank you very
I have
much.
it for my coffee. So they say that the productivity of a lab is proportional to the quality of the coffee machine. And then it's good to have good months.
Can I take a picture?
Sure.
Of course. Or send it to Kenji? Yes, of course.
Thank you.
If you were supposed to take pictures during the whole time.
No, I didn't.
That's what Kenji said we were supposed to do. Okay.
But thank you for having me. I've had a great time both here and then in Rio and then Petros. It's been great, and I regret not having come here earlier and not having more time to.
Hopefully from this visit you will get some collaboration.
Yeah, no, I'm looking forward to that. And again, for the students in particular, if you're looking for your internships, look at our website. It's a bit early for that season. We don't need to, but generally because it's convenient for students, we synchronize our cycle with having interns in the summer. But if you want to come at any other time of the year, we have openings. Typically our openings start going out maybe in a month or two, and most of them are out by the end of the year. So take a look, go to merle.com and go to our website, and there's a button called opportunities or positions or something like that, and you can see about it. And again, having students from abroad is not necessarily a big problem. It's just a bit of extra cost for us.
Thank you again.
Thank you.